going to talk about my own approach to building thinking machines, which is currently instantiated in an open source software project called OpenCog. In the 10 to 12-minute talk, I'm not going to be able to tell you too much about it. I'll give a high-level overview, and you can look online for more information. So in one sense, it's similar to a bunch of other cognitive architectures out there, including arguably SOAR, ACT-R, and so on. It's an integrative architecture. It can be depicted as a bunch of boxes with lines between them with different kind of knowledge stores and learning processes associated with the different boxes. I mean, it's which distinguishes it from, say, a spiking neural net model of cognition or a logical theorem proving model or something. This is not a very satisfactory boxes and lines diagram, but none of them really are ultimately. I mean, we have different kinds of memory in the system, different ways of representing declarative memory, procedural memory, sensory memory, episodic memory, and so forth. We have a perceptual hierarchy, which is used as a hierarchical temporal memory system, which is Itamar Erl's Destin system, which was developed separately and is now being integrated with OpenCog. And we're also using Itamar's stuff for a goal hierarchy. And each of these types of memory has associated with it certain learning mechanisms. So say declarative knowledge is associated with a probabilistic logic engine called PLN, probabilistic logic networks, which has some similarities and some differences from standard graphical models and Paul's factor graph stuff and so forth. And we have also other heuristics acting on declarative memory, such as conceptual blending. For procedural knowledge, we do use evolutionary learning, which, however, is quite distinct from what Randall was mentioning. We're not trying to evolve the whole architecture. We're using a sort of probabilistic evolutionary learning called Moses, developed by Moshe Lux, to evolve procedures fulfilling certain functions. But that's within the overall architecture, which is fixed. And for allocation of attention within the system, we use something called economic attention networks, which is vaguely similar to activation spreading in an attractor neural network, but the mathematics is based on economics rather than trying to mimic the precise equations of neural electricity propagation in the brain. So there's a lot going on here, much more than I'm going to describe in a minute or so. But there's multiple memory stores for different types of knowledge, different learning mechanisms associated with the memory stores. The most central knowledge store is the declarative knowledge store, which is called the atom space, which is a weighted labeled hypergraph, consists of a bunch of nodes and links. Most of the nodes and links have probability values attached to them, which can have different interpretations depending on the type of node or link. The nodes or links also have attention values attached to them. For example, short-term importance values, denoting how important it is to the system to think about that node or link at a certain point in time. Long-term importance values, connoting how important it is for the system to maintain those nodes and links in the system's memory. One of the key theoretical ideas underlying the system, which is not necessarily unique to our system, but maybe emphasized more in our system than others, is a principle I call cognitive synergy. And this is rooted in the commonplace observation that the worst problem facing AI is really combinatorial explosion. If you didn't have to worry about the combinatorial explosion of possibilities, some fairly simple algorithms would let you achieve vast levels of intelligence. And Marcus Hutter's AXE algorithm, as Suzanne mentioned, being one of them. And our declarative learning algorithms, probabilistic logic networks, they work well on small problems, and when we scale them up to large problems, they can get baffled by the large number of possible inference chains there are to follow. Similarly, procedure learning, using our Moses evolutionary learning system, works great for small problems, and then if you're trying to evolve procedures, as the procedures are trying to evolve get bigger and bigger, there's a combinatorial explosion of the number of possible procedures. And one of the theoretical notions underlying this design is that the learning algorithms corresponding to the different types of memory should help each other combat their intrinsic combinatorial explosion. So that when, for example, Moses runs into a problem searching procedure space, it can then turn to PLN, probabilistic reasoning, and do some declarative inference, which can, for example, help it do reasoning like, okay, what kind of procedures worked on similar learning problems before? So I'm trying to learn to juggle apples. Well, okay, I don't know how to juggle apples, but I've had to throw stuff up and catch it before. Declaratively, what can I transfer from these previous similar throwing and catching problems? Then you're using declarative knowledge to do uncertain transfer learning, to transfer knowledge from a procedure learning problem to another procedure learning problem. And there are many, many other examples of that. This kind of thing can happen in many other AI architectures as well. We've placed a particular focus on it in our own work. We haven't made virtual humans of any sophistication yet. We've worked on virtual dogs in a virtual world. And I'm not going to show much of the video here due to lack of time, but this is in the multiverse virtual world. The AI controls the dog. The human characters are controlled by people. The thought bubbles were just drawn on afterwards to show some of the nodes and links that the dog perceives related to various objects in its environment. And what happens here is the dog's trying to learn to play fetch, for example. So the people are playing fetch, and the people say, hey, I'm playing fetch. The dog watches what they do, and it notices they've associated the word fetch with the activity they're carrying out. Then when the dog says, okay, then when the people, rather, tell the dog, okay, play fetch, it is associated or grounded the word fetch with what it saw. And I didn't hook the audio up, but you can imagine. The dog goes woof, woof, woof. It's understanding only a very limited subset of English here. There, it tried to play fetch wrong. They said it was bad. It got an inheritance link in its logical knowledge base between me and bad, surely to traumatize it in its future life. Right? So now, okay, it brought the ball correctly. Good. Now, learning fetch in this limited environment is very easy for a suitable AI system because there's not such a great combinatorial explosion of possibilities. There's not that many objects there. There's not many things the characters can do. So in a sense, it's sort of a toy problem. And to make a really impressive demonstration, you'd even need a much richer virtual environment, or you want to have a robot dealing with a rich environment that's not just a robot lab, and with many, many possibilities, many affordances, both to make the learning problems more difficult and to give more data for transfer learning and reasoning and concept learning and so forth. But what we do get from this sort of simple experiment is similar to, as Paul described. I mean, you get perception, you get action, you get language, you get social interaction, you get emotion. So you get learning. You get a sort of full gamut of the types of experiences and capabilities that a real agent needs to carry out human-like intelligence. It's all just a bit simplified because it's in this virtual world. And we're carrying on that work now together with Jino Yu, who will speak a little later today, in Hong Kong Polytechnic University, working on going beyond the virtual dog to make virtual humans that can live and learn in a virtual world. And one distinction from Paul's work, which is also very interesting, is that learning is really at the core of our system, where the first thing we did is make a learning mechanism associated with each kind of memory. So with our virtual humans, they will use language and language generation and language comprehension and reasoning and so forth. But the focus is on having them learn in the virtual world from the humans interacting in the virtual world. We also have another project using the same code to try to control a humanoid robot, which currently is less advanced than the result with the work with animated agents, because working with a robot is harder. I mean, this is work being done at Xiamen University in Xiamen, China. We're working with a simple Now robot, which is not a robot we built. It's commercially available. Essentially, we take the system used to control virtual dogs and virtual humans, and we add on to it visual perception, auditory perception, and multi-level actuation, which, of course, is a big deal because you can't just take perception and like graft it on to your AI system. You need feedbacks between the perceptual layer and the cognitive layer. And let's go. So I'm not. This video is longer and more boring than the other one because robots are annoying to work with. But also, the sound would be really good here. Well, oh well. There's some Chinese guy in here, and he's saying, "Go to the table." And then it's going to that table. Or no, I think he's saying go to the chair, actually. then he will tell the robot to go to the ball, and he will go to the ball. And so what you have there, you have basic speech processing, then it goes into the language engine. The robot sees the objects around it, and it's still a toy environment because it's a robot lab without too much stuff there. That robot, I mean, the Now can't climb stairs, and if it had to recognize a chair in this environment with clutter around and bad light, it wouldn't do so well. So I don't think, as Adrian said, this is a long way from being able to do anything but amuse you in your own home. On the other hand, now the guy told him to go to the ball. I think he's going to go get the ball. But nevertheless, from a research point of view, it forces you to grapple with problems that virtual worlds don't. And so far, it's been more integrating vision systems and movement systems with our cognitive engine. But the next step is to put some more interesting feedback in there. So what we really need to do is take a hierarchy, a perceptual motor hierarchy, and link it in with the atom table, which is our primary knowledge representation in this system. Actually, I just realized this is an old version of my presentation. I have a better version of that slide somewhere. Maybe. No? Yes. Woohoo. All right. So here we have Itamar Errol's hierarchical deep learning architecture, which is, it's vaguely similar to Jeff Hawkins' hierarchical temporal memory system, but at the present time, my observation is it appears to be significantly more functional, and it does pretty well at image and video classification and understanding. And Itamar is attempting to develop this into a full-fledged general intelligence architecture, and he talked about this at the H+ Summit at Harvard. What I'm doing is I have a student taking his system and linking it in with the declarative knowledge base in OpenCog. So we're linking in what is observed in the hierarchical temporal memory with conceptual knowledge in our weighted labeled hypergraph, which doesn't mean I don't, maybe he could go all the way with just his system. I'm not saying he can't, but I think it's interesting to hybridize between the two of them. And there's a lot of subtlety here, because his hierarchical temporal memory, vaguely similar to Hawkins, it's making probabilistic judgments. So each level here refers to a smaller region of space-time. As you go further up the hierarchy, you have modules dealing with larger and larger regions of space-time. A module here is trying to predict what will happen next in a certain region of space-time. A module here is trying to predict what will happen next in a certain larger region of space-time. And inside each module, you're doing some EM clustering and some prediction to try to model what's been happening in that region of space-time. Then you're making a probabilistic judgment about what's going to happen next. And so in the integration, what we can do is use the knowledge in our cognitive knowledge store in OpenCog to bias these probability judgments of what's going to appear, which can be really helpful. Like if you're looking at a blurry scene, your cognitive knowledge can help you interpret it. On the other hand, the state of this hierarchical network, to map that into conceptual knowledge, requires some other interesting stuff you have to do. You have to, in essence, you have to recognize the attractors, generally right now fixed point attractors, later maybe other ones. The attractors in this hierarchical network link those attractors in with conceptual nodes in the conceptual knowledge base. And this is a kind of linkage between lower level, like perceptual motor knowledge, and conceptual knowledge that becomes critical in dealing with robotic applications. And we can kind of finesse our way past it in the virtual world applications, because the perceptions and motions in the virtual world are more limited. Now, you could do this in a fully fleshed out virtual world as well, but you don't have to. And so there's always a reason to avoid it. So just to briefly connect this with my talk I gave yesterday on bioinformatics applications, what I'm hoping to do in the grand scheme of the rest of my career, pretty much, is we're working with OpenCog on kind of childlike AGI, humanoid robots on virtual characters in video games, which may be very good at doing some specific things, but are not probably going to be as smart as you and me initially. And we're working on narrow AI applications, primarily to bioinformatics, potentially to other scientific areas as well. But our software architecture allows the integration of these various things, which can lead to some rather interesting systems which will not, to use Randall's term, be AHIs. I mean, if they're not artificial humans, if you take ensemble machine learning for bioinformatics on the same weighted labeled hypergraph as you're using for a young robot or video game character, it's not human-like. On the other hand, it may be more useful than humans at doing science. The gamble is that we can take the common sense knowledge that you get from these robotics and video game applications and link that common sense knowledge with the specialized capability used for things like biology data mining. And because there's a common semantics and a common set of learning mechanisms to the two, that common sense knowledge from here can then help you better understand biology and better understand the other domains that machine learning deals with. And if all goes well, in that way, you get to some interesting AGIs that way, which are not artificial humans, but nor are they General Marcus Hutter style AGIs that can solve all possible problems but require infinite processing power. It's just a different class of mind that we're working towards. And so I'll conclude now, but we're working on all right, I'll just conclude.